Okay, so today we're multiplying polynomials. So we're going to skip down to Explore 1. This is truly just an extension of what you did in Algebra 1 when you learned to multiply monomials and binomials. When we multiply polynomials, we're going to be using a combination of the product rule for exponents and the distributive property. And so, ignore that. The product rule, does anybody remember this product rule for exponents? If I had two bases multiplied together and they were the same base, then I could add their exponents. All right? And then we'll also be using the distributive property. Does anyone remember what the distributive property is? What? So if I have something outside a parenthesis, I distribute it and multiply it to every item inside. All right. Okay, so we have a couple examples of multiplying monomials here. If I had 5x times 6x cubed, I multiply the 5 and the 6 because they're both coefficients. So the coefficients are just straightforward multiplication. 5 times 6 is 30. But then on the variables, I add their exponents. So x has an exponent of 1. X cubed has an exponent of 3. So we add together 1 plus 3. And that's where they get 30x to the fourth from. All right, so on the next one, I have negative 2x squared y to the fourth z times 5y squared z. So I'm going to multiply negative 2 and 5 together. Negative 2 times 5 is negative 10. Then I'm going to multiply x squared times, oh wait, there's no other x's. So x squared hangs out by itself. It doesn't combine with anything. Y shows up twice, so we add its exponents. So since I have exponents of 4 and 2, I add together 4 and 2. And then z shows up twice, and both times you don't see an exponent. If you don't see a number on a variable, it's an exponent of 1. When you don't see an exponent on a variable, it's an exponent of 1. And so that's where they got z to the 1 plus 1 from. That's where they got z to the 1 plus 1 from. So overall, that simplifies down to negative 10, x squared, y to the 6, z squared. Helmets applicated. Thank you very much. Okay, sure. All right. So I have 2 plus 3x times 1 plus x. This is a different example. What if I had, instead of a monomial times a monomial, what if I had a binomial times a binomial? Bi means 2, so binomial means 2 terms. So it's just the idea of the distributive property. I take my polynomial and I distribute it to each item in the other parenthesis. So that's why you see 1 plus x occur twice. Now the book did something without explaining it here. They took 1 plus x and they rewrote it as x plus 1. Do those mean the same thing? Yes. Commutative property of addition tells me I can reorder addition. So that it probably would have looked a little nicer if they'd left that as 1 plus x. All right, but they don't have to because of the commutative property of addition, but they do mean the same thing. And so that's distributing once, but we still have parentheses in this problem. So since there's still parentheses in this problem, you can go and distribute again. But this time you're taking the number on the outside and distributing in. So now it's creating a total of 4 terms that we can then reduce. So the result of that one was a trinomial. Tri means 3 terms. Okay, trinomial. So we're going to be practicing today with going beyond a 2 by 2. When you were in Algebra 1, the highest you went was a binomial times a binomial. Today we'll introduce the idea of multiplying by a trinomial. All right? So, all right. So we start by now the book decides to reorder to standard form first. That's optional. Okay, your final answer I would like to see in standard form, but you don't have to reorder in standard form to be able to multiply. If you like that and you find it helps you organize yourself better, feel free. All right, but you do not have to do that. Once I have my structure, rather than having to show that distribution in separate steps, I can do all my distribution in one step. And so that's what I'm going to do right here. I'm going to start with my x. And I'm going to take x from my first binomial and distribute it to every item in the next polynomial. But how many items are there?
3.
So I have to distribute it 3 times. Not just 2, 3 times. So that's where 2x squared, x times negative 4x, x times 1 comes from on the next line. Then I take my 2, and I have to distribute the 2 to every item in the next polynomial. So I distribute it once, twice, 3 times. And that's where 2 times 2x squared, 2 times negative 4x, and 2 times 1 is coming from. So have I taken care of every item in the first polynomial?
Yeah.
And I've distributed it to every item in the second one. All right, so that's our distribution property extended to multiple terms. So it's really no different than what you did in Algebra 1.
So why don't the teachers like to call it FOIL?
Are there only 4 terms here?
Oh, okay.
There's 6. And so that's the danger with FOIL. FOIL only works if it's a binomial times a binomial. Now you have first, you have the outer inner, you have the outer, and so where if you just emphasize distribution, you can expand distribution to any number of terms. But so FOIL is a method for, but you have to know it only works for binomial times binomial. So that's a great question though. All right. And so then we just reduce, so x times 2x squared is 2x cubed. So they're just combining the powers on each of them. So then you want to look for like terms. So like 2x cubed, are there any other x cubes? No, so it comes down into the answer. Negative 4x squared, are there any other x squareds?
Yes.
So what do? They cancel each other. X, are there any other x's?
Yes.
So 1x minus 8x is, and then 2, it's all by its lonesome self, so it comes down here to the answer. So it's just combining those like terms. So we're going to look at example B, but I'm not going to use the method the book uses. I'm just going to say the book's method is dangerous. All right, they use a vertical format that has a lot of room for error and would not be used in any true mathematical justification. So I'm not going to be using the method the book uses on example B. I'll use a different one. Now, last period, somebody found a connection of this to science. Can any of you think of something in science that is related to this kind of multiplication? Where you had to multiply like a variable by another variable and come up with a new term based upon it? What? Did somebody say something? Or is it just the Stace? What if you were like comparing a mom's eyes to a dad's eyes and trying to figure out the kid's eyes?
Oh,
What? Punnett squares. Punnett squares are multiplying variables, right? And you're really treating them as separate terms that you're multiplying. And the dominant and the recessive, or the two dominants, you're treating each of those as separate terms. And so we can actually use that model for multiplying our polynomials. All right, so somebody found that connection last period and I liked it, so I'm going to go ahead and show you how to use that for these. And we'll do that on example B instead. It's actually based upon the concept of area, because like when you're doing a Punnett square, it's usually a square, right? And so what's the area of a square? Well, the side times the side. And so that's how you find your new genetic traits, is by multiplying side by side, which is just a formula of a square. So we can expand it even to be a rectangular shape. And in a rectangular shape, what's the area of a rectangle? Length times width. All right, so we're going to create a rectangle here. And since my first polynomial has two terms and my second polynomial has 3 terms, I'm going to make it a rectangle that's 2 high, and I'm going to make it 3 wide. Now, if you wanted to make it 3 high and 2 wide, that would have been fine as well. But so I'm making a rectangle that's broken into segments based upon having a binomial times a trinomial. And I'm going to assign each part of the binomial to its own row. So there's 3x and negative 4 get their own row. Then I have 2x and negative 7x squared each get their own column. And so we're going to find the area. And so area is length times width, or base times height. So what is 3x times 2?
6x.
So there's 6x. What's 3x times x? 3x squared, good. What is 3x times negative 7x squared?
Negative 21x cubed.
All right. Then I have negative 4 times 2.
Negative 8.
What's negative 4 times x?
Negative 4x.
What's negative 4 times negative 7x squared?
Negative 28x squared.
Negative 4 times negative 7.
Positive.
Positive 28x squared. So now we found the area of these rectangles in here. Now we're going to put all these pieces of these rectangles together to make the full one. And so I'm going to do it in standard form. So what's my greatest degree? Negative 21x cubed. So I'm going to start with that, negative 21x cubed. What's my next greatest degree? Squared. So I have 3x squared and 28x squared. What do they combine to be?
31x squared.
I have 6x and negative 4x. What do they combine to be? And all by his lonesome self, negative 8. Now you've multiplied polynomials. So the first one is just a distributive property. And the second method, we actually, in mathematics, we call it the area model. It's the area model because you're finding the area of each of those rectangles created by the pieces of the binomials. So either method is fine. Either method is mathematically justifiable. So feel free. Again, they're showing this vertical method. The vertical method leaves a lot of room for error. So I'm going to discourage it and not actually go over that with you. Okay? But instead, I'm offering you another alternative of the area method. All right, so I'm going to do number 3 with you, and then you guys will try number 4. So I'm going to use the distributive property. And because like when you get to really large polynomials, you're not necessarily going to want to draw a rectangle if it's like 5 by 6. That might become messy in itself. All right, so I do tend towards the distributive property, but when you're doing smaller ones, that area method is a nice organizational tool. So I'm going to start with 3, and I'm going to distribute my 3. 3 times 4 is? 3 times negative 7x is?
Negative 21.
3 times 5x squared is?
15x squared.
2x times 4 is?
8x.
2x times negative 7x is?
Negative 14.
2x times 5x squared is? Cubed. Cubed, because x and x squared make x cubed. All right, so now we want to combine our like terms. So what should come first? Good. What should come next? Actually, that was horrible. Okay, so 15x squared minus 14x squared was x squared, good. Then negative 21x and 8x make negative 13x. And then that leaves me with 12 on the end. So go ahead and try number 4. Try number 4. And if I have a volunteer to do it on the tablet. Any volunteers to do it on the tablet? Thank you, Emma.
Do I just do it now?
All right, do we agree?
Yes.
One caution, and so you don't really see a lot of negative exponents at your level, but that almost looks like an exponent of negative 18. So it threw me off for a second. So just be cautious. Make sure things look like they're next to each other and not exponents when you're submitting. But good job. All right. So that's it for today on notes. We'll do practice with it tomorrow. And now you're going to get a Chromebook. One Chromebook between 2 to 3 people. Okay, one Chromebook between 2 to 3 people. There is a document on Google Classroom you need to fill out. You only need one member of the group to submit it. If somebody else in your group is submitting it, then you as a private comment need to tell me whose document I'm looking at. All right? So if Emma's working with Destiny and Destiny submits the document, then Emma needs to say, see Destiny's document. All right? That way I know who's to look at for the results. And you're going to be going on Desmos to do this. All right? Talk it out with each other. It's 2 questions.